In this video, we're going to go over the solutions for this week's section handout on reinforcement learning. Let's start with the first question, learning in grid world. In this problem, we're given a very simple grid world shown here. We're asked to use temporal difference learning and Q-learning to find the values for the states in the grid. The transitions that we observe are listed here. So let's start off with temporal difference learning. First, I'll start with a small comment. As mentioned in lecture, generally we use temporal difference learning to calculate the values for a fixed policy pi. In this example, notice that we don't have a fixed policy since from state C, there are two transitions that take different actions. Those are C south and C east. For off-policy learning, we generally like to use Q-learning since we can associate values not just with the state, but with state action pairs. We can still do off-policy learning with temporal difference learning by following the equation here. It's just that now, since we're allowed to take different actions at a state, the values from these different actions contribute to the overall value that we learn for the state, and we might not exactly want this behavior. To illustrate this with an example, let's say we had two valid actions from state C here, that is to move north to A and to move south to E. Now assume that if we make it to A, we get some really high reward, say plus 100. And assume that if we go south and make it to E, we get some really low reward, say negative 100. Assume no discounting and no noise. If our episodes alternate between going north from C and then going south from C, we're going to get into this kind of ping pong behavior where when we visit A, the value of C shifts up, and then when we visit E next, the value of C shifts back down. So if the process keeps going on, we won't converge to the optimal value, which should be this plus 100 we have going north. The reason is because the negative value that we got from going south drags our value down. Okay, but nevertheless, let's perform TD learning with the transitions we have. The equation for the TD learning update is shown here. And remember, we update this each time we see a S prime R transition. So for this transition, we update the value of the state S. And the update is going to consist of two terms. The first term is the current value for our state S multiplied by a weight of 1 minus alpha, where alpha is the learning rate. And the second term is the sample reward we get for observing the transition. And like in MDPs, there's this immediate reward R and a discounted future rewards gamma times V of S prime. And this gets weighted by a factor of alpha. Initially, all of the values at each state are 0. I'm going to store them explicitly in this table here. So state and value state. Let's put A, B, C, D, and E, and then the corresponding values are 0, 0, 0, 0, and 0. So we process the transitions one by one in order. We start with the transition B, East, C, 2. The state that we started in is B, so we'll be updating the value V of B. And the way we're going to update it is by following this equation here. So the value of B is going to be set to 1 minus alpha times the current value of B plus alpha times the reward plus gamma times V of the landing state, which is C. And all we need to do is plug in numbers. So alpha is 0.5, that means 1 minus alpha is also 0.5. The current value of B in our table is shown here, that's 0. So we have 0 here, plus the alpha value, which is 0.5, times the reward. The reward for this transition is 2, so 2 plus gamma, that's 1, times V of C. The value of C in our table is 0, so we put a 0 here. This gets simplified to 0.5 times 2, which is equal to 1. And so we update the value for B in our table to be 1. The next transition that we have is C, South, E, 4. Here, since the starting state is C, we're going to update the value for C, and that's going to be set to 1 minus alpha times the value at C plus alpha times the reward plus gamma times v of the landing state, which is e. Here, 1 minus alpha again is 0.5. The value of c is currently 0. Plus alpha 0.5 times the reward. The reward for this transition is 4. Plus gamma, which is 1, times the value of e. Currently in our table that's 0. So we have this. This gets simplified to 0.5 times 4, which is equal to 2. And so we update the value for c to be 2 in our table here. Our next transition is C East A6. Again, the starting state is C, so we'll update the value for C. That's going to be 1 minus alpha V of C plus alpha R plus gamma V of the landing state, which is A. Putting in numbers, 1 minus alpha 0.5. The value of C was previously updated to 2, so we're going to use the new value of 2 here. Plus alpha 0.5 times the reward, which is 6, plus gamma 1 times the value at A. Currently that's 0, so put a 0 here. This gets simplified to 0.5 times 2 plus 0.5 times 6, which is equal to 4. So we update the new value for C to be 4. The final transition that we have is B East C2 again. Again, we're going to be updating the value for the first state that we're in, so that's the value for B. That's going to be equal to 1 minus alpha times the value of B plus alpha times the reward plus gamma times the value of the landing state, which is C. And again, we put in numbers, 1 minus alpha, 0.5. The value of B, currently that's 1. That was from our initial transition here. So we use the value of 1 we have, plus alpha, which is 0.5, times the reward, that is 2 here, 2, plus gamma, 1, times the value at C. The value of C is currently 4, so we'll use the value of 4. And this simplifies to 0.5 plus 0.5 times 6, and so we get 3.5. We'll set the new value for B to be equal to 3.5 in the table here. And so we're done. The final values that we get are that the value for B is 3.5, the value for C is 4, and the values for A, D, and E are 0. Next, we'll run Q-learning with the same set of transitions. Here's the equation for Q-learning. It's pretty similar to TD learning, but now we're learning the Q values instead of the V values. Again, the update consists of a sum of 2 values. The current QSA value that gets weighted by a factor of 1 minus alpha, plus the sample reward that gets weighted by a factor of alpha. Notice that the sample reward is written slightly differently than what we saw in TD learning. In TD learning, what we saw was that the sample reward was the immediate reward R plus the discount times the value at the landing state. Well, this term here is exactly the value of the landing state, because to calculate the value at the landing state, you have to take a max over all Q values from that landing state, and that's what this term is. Initially, all of the values at each Q state are 0. Since there are a lot of Q states that are possible, I'm not going to explicitly keep track of all of them, but let's nevertheless create a table. Let's put the state action pair here and the Q value for that state action pair. And what we're going to say is that if a Q value is not present in this table, it's by default set to 0. And if it is present in this table, we'll just look up what the Q value is. So again, we process the transitions one by one in order. We'll start with the transition B East C2. And since the starting state for this transition is B and the action taken is East, we're going to be updating the Q value for B and East. According to the Q-learning update equation, this is going to be set to 1 minus alpha times the current value for Q of B East plus alpha times the reward plus gamma and we take the max of A prime, that is all actions starting from the landing state, and the landing state for this transition is C. So we have C A prime. Plugging in values, 1 minus alpha is 0.5. Q of B east, well, B east is not in our table, so it's currently 0. Plus alpha, that's 0.5. The reward is 2, so 2 here. Gamma is 1. And then we need to take a max over all possible actions of the Q states that begin with C. Well, we don't have any values in our table here, so this is definitely going to be 0. Simplifying this, we have 0.5 times 2, which is equal to 1. And so we set the value for Q of B east to be 1. Let's write that in our table here. So we have B east, and the value will be 1. Our next transition is C south, E, and 4. The starting state for this transition is C, and the action taken is south, so we'll be updating the Q value for C south. And that's going to be set to 1 minus alpha times the current value for Q of C south, plus alpha times the reward plus gamma, max over all actions A prime of the Q values starting from the landing state, which in this case the landing state is E, so E A prime. Plugging in values, 1 minus alpha again is 0.5. The Q value for C south is not in our table, so the value is 0. Plus alpha 0.5. The reward for this transition is 4. Plus gamma is 1. And then we want a max of all Q values beginning at E. Well, we don't have any tuples here starting with E, so the value here is 0. This gets simplified to 0.5 times 4, which is equal to 2. And so we create a new entry here, C south, and that's going to be set to a value of 2. The third transition that we have is C east A6. In this transition, we begin at state C, and we take the action east, so we'll be updating the Q value for Q of C east. That's going to be set to 1 minus alpha times Q of C east, plus alpha times R plus gamma max over A prime of Q of the landing state, which is A, and then action A prime. Okay, so we put in values here, 1 minus alpha 0.5. Q of C east. Well, we don't have an entry for C east here. We do have an entry for C south, but those are two different entries, so we can't use this value. So the value for Q of C east is going to be 0, plus alpha, that's 0.5, times the reward. The reward for this transition is 6, plus gamma, that's 1, and then a max over all Q states starting from A. Well, we don't have any entries that have state A in this table here, so the value is 0. Simplifying this becomes 0.5 times 6, which is equal to 3. And so we create a new entry, C east, and we set its Q value to 3. Okay, so we're finally on our last transition, B east C 2. So we started from B and we take the action east, so we'll update the Q value for B east. That's going to be set to 1 minus alpha times Q of B east, plus alpha times the immediate reward plus gamma. Then we take a max over all actions A prime of the Q value starting from the landing states, which is C. We plug in values, so 1 minus alpha 0.5. Q of B east. Now we have an entry in this table which has a value of 1, so we're going to use that value of 1 here. Plus alpha, that's 0.5, times the reward for this transition, that's 2, plus gamma, 1. And now we take a max over all Q values that start with C. That's going to be a max over, let's see what we have. So we have two different positive Q values that start with C. Let's consider them both. So we take the Q value for C South, that's 2, and then the Q value for C East, that's 3. And simplifying this, we get 0.5 plus 0.5, so 2 plus 1 times max of 2 and 3. Max of 2 and 3 is 3, so this evaluates to 5. And so adding this up, we get a value of 3. And so we update the entry for B East to B3. And now we're done. So the final Q values that we have are that Q of B East is 3, Q of C South is 2, Q of C East is 3, and all other Q values are 0. Alright, moving on to question 2, Pacman with feature-based learning. In this problem, we're going to work with approximate Q learning, which means we won't have Q values for every state action pair, but rather we keep around a general function. To start, to the bottom left here is a small recap of the equations used for approximate Q learning. Our Q value is now a linear combination of features, each with its own weight, and we'll be trying to learn a good set of weights for these features, so that's the goal. For a given SA'(R) transition, our update looks as follows. We compute this difference term, which takes into account the sample reward that you've seen in Q learning, minus the Q value for the state action pair. Notice that to compute this value and this value, you have to use this linear combination that you have here. Then after that, for every weight, we're going to update the weight by this update term here. It consists of 3 parts: the learning rate, the difference term that we just computed, and the value of the feature corresponding to the weight that we're currently updating. The 2 features that we're going to consider for this problem are shown here. It's going to be f sub g, the number of ghosts next to Pacman, and f sub p, the number of pellets next to Pacman. The state we're considering, that is state S, is this configuration here. And for the first problem, we're asked to compute the feature values corresponding to this state. So the feature value for the ghosts, the number of ghosts next to Pacman, well, there's just this red ghost and this light blue ghost, so the answer is 2 here. For f sub p, we want to count the number of pellets next to Pacman. There's this 1 pellet north of Pacman, so the answer is 1 here. One thing to keep in mind is that in the Q function, the features that we have depend on the state action pair. So to be pedantic about the notation here, we should put for question 1 that there's a state action pair involved. However, these features that we have for this problem, they don't depend on the action taken, they only depend on the configuration on the state. And so for this problem, the action's not going to play much of a role when we compute the Q values and do the updates. In the general case, this is not true, so please keep that in mind. For the second question, we're asked to compute the Q value for the state, given that the weights Wg equals 100 and Wp equals -10. So to compute the Q value, we use this equation here. It's going to be a linear combination of the features. We have 2 features, so it's going to be the weight of the ghosts times the feature value of the ghosts for the state action pair, plus the weight of the pellet times the feature of the pellet for the state action pair. We can just put in numbers. The weight of the ghost is 100. The feature value for the state action pair of the ghost is here, that's 2. Plus the weight of the pellet is -10, and the feature value for the pellets is 1. This simplifies to 200 minus 10, which is equal to 190. For the third question, we received a transition SA'(R). And we know that the reward we got for this transition is 50. We also know the feature values at the landing state. So the feature value for the ghost of the landing state, and let's attach some action here. Remember, it doesn't really matter what the action is because the features only depend on the state. The feature for the ghost is going to be 0. The feature for the pellets is going to be 2. And we know that the discount factor is 0.5. In this question, we're asked to compute the new estimate of the Q value. This term is a little bit misleading. What we really want you to do here is to compute the sample reward, which is this term here in the update equation. The sample reward, according to this equation, is r plus gamma max a prime q s prime a prime. But as we mentioned, the action doesn't really matter. No matter which action you take from the landing state, they're all going to have the same q value. So in this problem specifically, the equation gets simplified to r plus gamma times just the q value at the landing state attached with some action a prime. So we can rewrite this part using this equation up here, and this is going to be r plus gamma times the weight of the ghost times the feature of the ghost of s prime a prime plus the weight of the pellet times the feature of the pellet s prime a prime. And let's put in numbers here. So r is equal to 50, gamma is equal to 0.5. The weight of the ghost, that's still 100. The feature value of the ghost at state s prime, that's here, that's 0. So let's multiply this by 0. The weight of the pellet, still negative 10. And the feature value of the pellet at state s prime is 2. So we have 2 here. Simplifying this is just 50 plus 0.5 times negative 20, and that's equal to 50 minus 10, which is 40. The last question asks us to perform the weight update, which concludes the round of approximate Q learning. So we're given that the learning rate alpha is equal to 0.5. So we calculated the sample reward at step 3. Let's finish calculating the difference term first. So the difference is going to be equal to the sample reward minus the Q value at the state action pair. The sample reward, as we calculated at part 3, is 40. The Q value for the state action pair, that's what we calculated at step 2. That's 190, so minus 190. And simplifying this, we have negative 150. Now that we completed the difference term, we can get to the weight update equation. We have two weights, so we need to consider both of them. Let's start with the ghost weight first. So the ghost weight, let's set that equal to the current ghost weight plus alpha times the difference times the feature value for the ghost of the state action pair. The original weight for the ghost is 100. Our alpha value is 0.5. The difference that we just calculated is minus 150. And the feature value of the ghost for the state action pair, that's what we calculated in part 1. So that value is 2, shown here. Multiply this by 2. Simplifying this, we have 100 minus 150, that's equal to negative 50. We can do the same thing for the pellet feature, so W sub p set to W sub p plus alpha times the difference times the feature value of the pellet times of the state action pair. The original value for the pellet weight is negative 10, alpha is 0.5, our difference term is negative 150, and the feature value for the pellet is 1. And so simplifying this, we have negative 10 minus 75, that's equal to negative 85. And we're done with the weight update. Notice that the weight of the ghosts here is now negative, which makes sense since we want to avoid the ghosts. The weight on the food pellets has become more negative, but at least the difference between the two is much lower now.